So welcome to your first set of lecture notes with Mr. Chen, and what we're going to be talking about is a different look at stoichiometry. Now, in honors chemistry, you learned about the T-bar method with dimensional analysis, where you would make the T-bar like this, and you would put take 10 grams here, and then you would say for example, 1 mole and 1.08 gram. Okay, well, I want you to forget about doing it this way. Okay, I want people to understand more about what moles mean and what conversions mean and these quantities are. So that's why we're calling this a different look at stoichiometry. Now, the AP handout gives you these formulas. Okay, it says right here that N, which is the number of moles, is equivalent to the mass divided by the molar mass. Okay, and molarity, which you learned about in honors chemistry, is the moles of solute per liter of solution. So molarity equals mole over liter. And make sure you understand that you can also rearrange these equations. So if you take the number of moles, N, and then you multiply it by the molar mass, that would give you the mass of the object itself. Okay, which makes sense because if you have 3 moles of something, for example, and the molar mass of an object is, let's say oxygen, which is 16 gram per mole. Okay, and remember when we say per mole, we're saying per 1 mole. So if you have 3 moles of a substance and you multiply it by 16 grams for every 1 mole, it would make sense that you multiply these, canceling out the mole units, so that you would say that your final mass would be 48 grams. Okay, so by the same token, if you take the mass of the object and divide it by the molar mass, that would tell you how many moles there are. Okay, if you look at the molarity formula, you should also take advantage of the fact that if you know that you have the liters times it by the molarity, which is the moles per liter, that's also going to give you the number of moles. Okay, now remember, they give you these these formulas on the AP handout, so you really shouldn't have to memorize any of these things, just like you really shouldn't memorize most of Western chemistry. Okay, so moving on, let's see if you can apply your knowledge and your understanding. Okay, how many moles of C5H12 are present if there are 9.3 times 10 to the 24th? And let's go ahead and correct that here and say 10 to the 24th atoms of hydrogen present. Now, I do not want you using the T-bar at all. Okay, I'd rather that you be thinking about what all this means. Okay, so you should draw on your knowledge from the summer assignment as well as from honors chemistry that if you have 1 mole of something, that means you have 6.02 times 10 to the 23rd particle. Okay, so let's think about this right here. If you have 9.3 times 10 to the 24th atom of hydrogen, okay, we can determine how many moles of hydrogen there are. Okay, and how do we do that? You would divide it by Avogadro's number. So we divide it by 6.02 times 10 to the 23rd atom per mole. Okay. And when you put that into the calculator, you will see here, I'm going to go ahead and run that calculation here and see that it gives you 15, I'm not going to wait too much about 6 fix here, but let's say 15.4 moles of H. Okay. But remember here, the question is asking you for how many moles of C5H12 are present. So if you're looking at the formula, for every 1 mole of C5H12, you are going to have 12 mole of hydrogen. So if you have 15.4 moles of hydrogen, you would divide it by 12 to find out how many moles of C5H12 there are. So we can say 15.4 divided by 12. To say we have roughly 1.29 moles of C5H12. Okay, but it's very, very important that you consider these mathematical relationships, such as this one right here. I'll go ahead and highlight that to make sure you understand this. And also understand these proportions so that you can think proportionally and in terms of quantity. Okay, so let's move on to the next problem, which is sample problem B. How many moles of iron are required to produce 8 moles of iron 3 oxide according to the balanced chemical equation below? Okay, so what you want to do here with stoichiometry is you want to focus on the mole to moles ratio. Okay, so let's look at the mole to mole ratio between iron 3 oxide and iron. Okay. If you look at the balanced equation, for every 2 mole of Fe2O3, you have 4 mole of Fe. So according to the given problem, if you have 8 moles of Fe2O3, how many moles of Fe will be given? So if you look at the ratio, it's a 2 to 4 ratio, meaning if you reduce that, that would be a 1 to 2 ratio. So in this case, you would multiply the 8 by 2. And ask yourself if that makes sense. Because when you multiply 8 by 2, you get 16 mole of Fe. And that would be here your final answer. Okay. Now, if you made a mistake, for example, if you multiplied it by 1/2 instead and divided by 2, let's say you did that, and you got here, we'll say divided by 2, and you get 4 moles Fe, that wouldn't make any sense because here you have 2 to 4, implying that there's more Fe than there's Fe2O3 in terms of moles. But this number would not make any sense here because here you have more Fe2O3 as opposed to Fe. So if you pay attention to your quantity and refer back to the balanced equation, it should make more sense that way. Okay, so your final answer on this one here would be 16 moles of Fe. Okay, so let's look now at sample problem C now. And we're going to add the grams in here at this point. How many grams of iron 3 oxide will result from 2.5 grams of oxygen according to the balanced chemical equation below? Okay, so this would be a good way for how you want to show your work. You want to go to moles first, no matter what. So we're going to take the 2.5 gram of O2, and you convert it using that formula that we looked at earlier. The number of moles equals the mass divided by the molar mass. So if we have the mass, 2.5 grams of O2, divided by the molar mass of O2, which is 32 grams per mole, okay, you can cancel out the grams unit so that your final unit will be in mole. And we go 2.5 divided by 32 gives you approximately 0.078 moles O2. Okay. Now, we have to convert it to moles of Fe2O3. So if you look at the fact that for every 3 mole of O2, you have 2 moles Fe2O3, according to the balanced equation that you see. So that means if you have 0.078 moles O2. Okay, now let's think about this. You want it to be a smaller number than 0.078 because when you look at the mole ratio, this is 3 to 2. So this number here needs to be smaller. So we could either multiply this by 3 over 2 or 2 over 3. And it would make more sense to multiply it by 2/3 because that's the smaller quantity, the result in a smaller quantity. And that would give you 0.052 mole Fe2O3. Okay. Now, since the question is asking you for the grams of Fe2O3, we need to convert that mole quantity to Fe2O3 to gram. So we can go 0.052 mole times the molar mass, which is 159.7. Remember, it is gram per 1 mole. And that would give you a final answer of 8.3 grams Fe2O3. And I realize that this is probably more time consuming, and you may not be wanting to learn a new method, but trust me, it makes a huge difference when you're taking AP chemistry because students have a lot of trouble understanding stoichiometry. And you'll see what I mean, when you take some of the review quizzes that you'll be taking throughout my class. All right, so this is when the new method of doing stoichiometry becomes useful, the limiting reaction problem. So for a limiting reaction problem, I highly recommend that you use the table method because the table will help you determine how much of the excess reaction remains. Okay, it also helps you fill out all the information that you need very quickly. So the question is asking you for how many grams of water will result if you have 40 grams of the propane and 50 grams of oxygen. So what we need to do is convert the 40 grams of propane to moles and the 50 grams of oxygen to moles. So go ahead and do that. I'm going to go ahead and pause the video and try this out, and then let's check base in a moment. So if you did this correctly, you would have gotten 0.909 moles of the C3H8 and the 1.563 moles of the O2. So I'm going to go ahead and fill that into the table. 0.909 mole and 1.563 mole. Okay, and the question doesn't ask you about anything with the carbon dioxide. So I'm going to go ahead and X out this column because we don't really need it. And it doesn't say anything about having any water in the beginning, so I'm going to put 0 moles of water. And you want to figure out how many grams of water there will be. Okay, now a bit of a shortcut to determine which one is limiting is you should determine what we call the moles of reaction. Okay, and that means that if you look at the balanced equation, I'm going to say for every 1 mole of reaction, RxN, that's equivalent to the coefficient, 1 mole of C3H8, and also 5 mole of O2. Okay. So if you have 0.909 moles of C3H8, and for every 1 mole of reaction, there's also 1 mole of C3H8. I'm going to go ahead and also put over here that also means that you have 0.909 moles of reaction. Okay. And then for 1.563 moles of O2, if you divide that number by 5, you get 0.313 moles of reaction. So, because this is the smaller of the two numbers between these two, this means that oxygen is your limiting reactant. So that means it's going to run out first. So I'm going to go ahead and put here minus 1.563 mole of O2, giving you 0 moles of O2 in the end. Okay. Now, to determine how many moles of water will be produced, okay, you can take that 1.563 moles of oxygen and convert it to moles of water using your coefficient. Okay, so let's go ahead and use the mole ratio to determine that. So I'm going to put a line right here to indicate that for every 5 moles O2, you have 4 mole H2O resulting. So 1.563 mole of O2. You times this by 4/5, you get 1.25 mole H2O. So that means that this will go up by a factor of 1.25 mole, leaving you with 1.25 moles of H2O in the end. Okay. We should also determine how many moles of C3H8 are consumed. So if you look that for every 5 moles of O2, you have 1 mole of C3H8. So if you have 1.563 moles O2, divide that by 5, you get 0.313 moles of C3H8 that are consumed. So we'll say this is minus, because that's being consumed, 3.13 moles. So in the end, you have 0.596 moles of C3H8. So to answer the question, how many grams of water will result if you have 40 grams of propane and 50 grams of oxygen? You're going to take that 1.25 moles of H2O and multiply it by the molar mass. So we say 1.25 moles of H2O times the molar mass of 18 grams per mole, and that's going to give you 22.5 grams of H2O. And that would be your final answer to that part of the problem. Okay, the limiting reactant part, we've already identified that to be oxygen, and how much of the excess reactant, which is the C3H8, remain, that would be the 0.596 mole of the C3H8. The problem doesn't ask you how many grams of the excess reactant remain, but if it did, you would take the 0.596 mole and multiply it by the molar mass to convert it to grams. Okay, so let's go ahead and move on to the next problem. So this problem is fairly similar to the one that we just did. It's another limiting reactant problem, but this time we'll give you a slightly different quantity. So go ahead and take that 5 grams of copper and convert that to moles. and also using your understanding of the molarity formula, using the milliliters here and the molarity, also convert that to mole. So go ahead and pause the video right now and resume once you've figured out that part. Okay, go ahead and verify your work and see that it matches what I got. And the next thing you need to do is to determine how many moles of reaction there are for copper and for AgNO3, so you can determine what the limiting reactant is. So again, pause the video and go ahead and see if you can determine the moles of reaction. Okay, so if you did that correctly, you would see that you have 0.0787 moles of reaction based on the copper and 0.04 moles of reaction based on the AgNO3. So what does that mean? It means that the AgNO3 is your limiting reactant, and that's going to run out first. Okay, and that's going to be 0 moles in the end. Okay. So how many moles of Ag will be produced? Well, if 0.08 moles of AgNO3 went in, you can look at the ratio. For every 2 moles of AgNO3 that goes in, 2 moles of Ag goes out. So that's a 1-to-1 ratio. So for every, even though it's a little bit repetitive, we can repeat this. For every 2 moles of AgNO3, that's 2 moles of Ag, 1-to-1. So we have 0.08 moles of this. That would also mean 0.08 moles of Ag will result. So this is plus 0.08. Okay. Now, again, we can say for every 2 moles of AgNO3, it gives you 1 mole of Cu must react. So for 0.08 moles, 2-to-1 ratio means you cut this in half. That'd be 0.04 moles of Cu. So this is minus 0.04 mole, giving you 0.0387 moles of Cu left over. So let's go ahead and convert the 0.08 moles of Ag to gram and the 0.0387 moles of Cu to grams. So go ahead and pause the video and try to finish up that last step. Okay, so let's verify that. You should have had 8.63 grams of Ag and 2.46 grams of Cu. Okay, quick pro tip, make sure that your change line, how much it changed by, matches the mole ratio. So this is 1 to 2, so 0.04 to 0.08 matches the 1 to 2 ratio. The 2 to 2, 1-to-1 ratio indicates that these are the same. Okay, so the change line must always, always, always match the ratio. All right, go ahead and finish up with the last problem right here. Problem F. Now, this is probably the most complicated of all the stoichiometry problems that you'll do in this class. You have here a precipitation reaction where you have 2 solutions mixed together to form a precipitate. You have 200 milliliters of lithium sulfate with the concentration at 0.5 molar and 150 milliliters of barium hydroxide with the concentration at 0.2 molar. So when you mix them together, you're going to want to know which one is limiting and which one is excess, because you're going to have some ions left over in solution. And the question is asking you for how many grams of the precipitate will form and what is the concentration of each ion that remains in the solution after the reaction has taken place. Okay. So we bypassed the first step for you here, which is to write the balanced chemical equation and make sure you know your solubility rules. That's knowing about the fact that sulfates are insoluble with barium, and group 1 metals, such as lithium, are always soluble. Okay, so we have the balanced chemical equation first, and then you should also write your total ionic equation, not your net ionic equation, to know what all the ions that are involved in the reaction are. And of course, we don't break up solids, so we left this part, solid. We didn't break this up into a ion. So the first thing you need to do is use your understanding of the molarity equation to determine how many moles of lithium sulfate you have and how many moles of barium hydroxide you have. So let's pause the video and go ahead and do that first step. So check your work here. You should have gotten 0.1 mole of Li2SO4 and 0.03 moles of BaOH2. Now we have to determine how many moles of each ion you have. So you have to account for the fact that for every 1 mole of LiSO4, you have 2 moles of lithium and 1 mole of sulfate, SO4, 2 minus ion. So if you have 0.1 mole of Li2SO4, that means that you have 0.2 mole of Li plus, and you also have 0.1 mole of SO4, 2 minus. Okay. Again, by the same token, for every 1 mole of BaOH2, you have 1 mole of barium ions and 2 moles of hydroxide ion. So if you have 1.03 moles of BaOH2, it means you have 0.03 mole of Ba2 plus and 0.06 mole of the hydroxide. Okay, and what we care about is the grams of the precipitate that will form. Okay, and we can actually ignore the spectator ions, at least on the right side. Okay, so you'll see why in a moment. Okay, so when you look at the limiting reactant, you really want to look at the ions that make up the precipitate. So the 2 ions being, I'm going to highlight these, barium ion and sulfate ion. So the limiting reaction is going to come from one of those. So once again, if you can see that for 0.03 moles of barium, that's 0.03 moles of reaction, and 0.1 mole of SO4 2 minus is 0.1 mole of reaction. So because it's a 1-to-1 ratio, we can actually go ahead and assume here that barium, Ba2 plus, is the limiting reactant. So I'm going to go ahead and say that this is minus 0.03, and then this is minus 0.03 as well, because it's a 1-to-1 ratio. So in the end, you have 0.07 moles of the SO4 2 minus and 0 moles of the Ba2 plus. Okay, and then I'm going to put 0 moles here, and then also a 1-to-1 ratio. This will go up by 0.03 mole. Okay. Now, the spectator ions do not participate in the reaction. Okay, in the end, you're still going to have 0.2 moles of Li plus and 0.06 moles of the OH minus. Okay, so go ahead and determine from that 0.03 moles of BaSO4 how many grams that is. So go ahead and pause the video and determine how many grams of BaSO4 are left in the end. So you should have gotten 7 grams of BaSO4 precipitate that will form. Okay, then the next part is asking you what is the concentration of each ion remaining in solution. So we have to take into account that concentration formula is the same as the molarity. Molarity equals the moles over the liter. And the final volume of the solution will be when you add the 200 milliliters and 150 milliliters to give you 350 milliliters, which gives you a volume of 0.35 liters. So the Li positive concentration, I'm going to put that in brackets. Well, remember it was a spectator ion, so it doesn't change at all. We take the 0.2 moles divided by 0.35 liters, and that gives you 0.57 molar. The SO42 minus, which is kind of the excess ion, 0.07 divided by 0.35. Gives you 0.2 molar, and then the OH minus will be 0.06 mole divided by 0.35 liter, and that gives you 0.17 molar. And that would be a final answer to the part asking what is the concentration of each ion remaining in solution. Okay, so that's a wrap for the different look at stoichiometry lecture. There are practice problems available on Schoology if you would like to apply what you learned. And it's not going to be easy. I know a lot of this may be overwhelming or confusing, and you may think this is pointless, but trust me, it will help you in the long run, especially as we go deeper and deeper into stoichiometry. Okay, so happy studying, and I look forward to seeing you in August. Bye-bye.